6. B10. Right. So this question asks, one element has its first four ionization energies equal to 89.4 kilojoules per mole, 17.51.1 kilojoules per mole, 14.848 kilojoules per mole, and 21,004 kilojoules per mole. So one big thing, right, that you should be seeing is that there is a dramatic increase, right, at that point right there, right, going from the ionization energy 2 to ionization energy 3, there's a huge jump there. And so something is very clearly happening in terms of the electronic configuration. So if we think about, what it is that we're looking at, right, ionization energy 1 is going to be the equivalent of, your atom, right, I'll just refer to it as X, not M. Eraser. Right, is X, right, it's turned into X plus, and you lose an electron in that case, right? Ionization energy 2 is then X plus being converted into X2 plus with loss of an electron. Ionization energy 3 is then X2 plus going to X3 plus an electron, and then ionization energy 4 is then going to be X3 plus going to X4 plus an electron in that case. So looking through all of that right there, right, this jump right here, right, this is the breaking point in terms of like how dramatic of a change in energy you have. And there's two scenarios where that really ever happens. One is you're going to have a jump when you go from the lower ionization energy is being pulled out of the p block, and then you're going to have then the next jump is then where you start pulling it out of the s block elements, right? That's always going to be a jump where you're going from something that's only a single electron that's left in like a p or an s orbital to all of a sudden now the next one is going to be pulling one out of essentially filled orbitals. That's going to be a scenario. And then the other one is, right, going then from having a single s electron in your system and then pulling it out and then ending up with a noble gas configuration after that ionization energy, where then the following one, which is much, much higher, is then pulling it out of a noble gas configuration, which is going to be much, much more challenging in that case. And so looking at this right here, right, seeing that break happen after that right there, right, where you have 2 plus, right, that tells us that when that element is at its 2 plus, oxidation state, it has probably a noble gas configuration in that case. And so the ones that would have that then are going to be the alkaline earth metals, right? Because those, right, when they're in the 2 plus state, they're going to have a noble gas configuration in that case. And so then any, other electrons that you start picking off are all going to, then be for an even lower energy level, right, where you start having to pick them off of noble gas configurations. And that's not very favorable, and it's going to take a lot of energy, right? That's why you get that jump of, close to, 13,000 kilojoules per mole, right? That's a pretty considerable jump. Versus where after the first two, right, it goes from like 900 to like 1750, right? You're just slightly doubling there versus all of a sudden everything going up, eightfold or something like that, right? That's a pretty big jump. So it's going to be the alkaline earth metals is the most likely ones in this case. Now, somebody during GPS, right, had mentioned that why isn't it the second row of the transition metals or even the second row of the lanthanides in that case. And so it could be, right, you can use that reasoning. The big challenge really there is that when you're picking off those electrons, right, you're not picking off the d orbital electrons, you're going to be picking off the s orbital electrons anyways already from the get-go. And so you're going to do that in those cases. And so, in the case of titanium, right, titanium 1 plus, that electronic configuration ends up being, instead of it being 4s1 3d2, it ends up being 3d3. Right, and that has to do with the fact that as you start applying a magnetic field to the d orbitals and f orbitals, they actually get stabilized and they go down in energy in those cases, right below the s orbitals and stuff. And so it makes sense, right? I can see the reasoning there, right? But the the most reasonable one, especially for that dramatic of a jump, is going to be the alkaline earth metals, right? Because you're going from something, all of a sudden, turning it into a noble gas configuration, and then all of a sudden, pulling things out from a noble gas configuration, right? That's going to be unfavorable. Part B, among your choices of elements should be one for which you can calculate one of these ionization energies exactly. Which element is it and why, right? And so thinking about this right here, in this class, we've only really used one equation with which you can calculate, the energy levels of orbitals, right? And that's the Rydberg equation. And so, there's the Rydberg equation where you have the energy level is going to be equal to negative R times Z squared over N squared, right? There's the modified Rydberg where you have the Z effective, but then the problem with that is to calculate the ionization energy, right? You have to know what the Z effective is. And the way that you find out the Z effective, right, is from the ionization energy. So if you've already experimentally determined the ionization energy, right, that's not really going to work. Whereas for the Rydberg, right, because it's strictly for a one electron system, we don't have to actually know the Z effective, right? Because if there's only one electron, there's no shielding. So all the full, nucleus, right, all the entire Z is being, pulling on that one electron in that scenario. And that should allow us, right, to calculate then what the ionization energy is to pull out that last electron in that case. And so because we only have 4 ionization energies, right, the only one that makes sense then to get to a 1 electron system after the third ionization energy, right, would be beryllium in this case, right? Because beryllium goes, 1 plus, it turns into isoelectronic with lithium, right? 2 plus, it becomes isoelectronic with helium. 3 plus, it becomes isoelectronic with hydrogen. And then 4 plus, right, it's just simply only protons. There's no, there are no, electrons left in that case, right? It's just simply 4 protons hanging out in space, with some neutrons, obviously, right? But for that right there, right, you can calculate, right? You can do the BE, and that has to do, right, is that can use the Rydberg equation for the 4th ionization energy, since it is right, since BE 3 plus is a 1 electron system, right? That's the reasoning why that right there works. 4, right? So the last part right here, right? C, prove that the ionization energies listed are for this element, right? And so the way that we can prove that is we can use the Rydberg equation right here and calculate out what the energy level is based off of that right there, right? And then we can compare that to the ionization energy in our case. So if we go through with that, right, the energy of, the first level, right, the n equals 1 level in this case right here is going to be equal to negative, what is R again? 2.18. I'm just going to write down a simplified number of it, right? 2.18 times 10 to the negative 18 joules, right? That's going to be now multiplied by Z. So in this case, Z for beryllium is 4, right? So we're going to have 4 squared over, right? We're only going to be doing the n equals 1 level, so it's going to be 1 squared. And so if we plug that in, and so I'm going to have to do that in my little trusty calculator right here. Equals, so we have negative R times 4 squared divided by 1 squared. Right, so what I get here then is negative 3.488 times 10 to the negative 17 joules, right? So that's, right, the numbers aren't directly comparable, right, because they're not in the same exact units, right? The ionization energy I gave you is in kilojoules per mole. So if we want to convert that, all we have to do now in this case right here, right, this is per atom. So all we have to do now is just simply multiply 6, our value by Avogadro's number. So 6.02 times 10 to the 23rd atoms divided by 1 mole, right? And then also convert it into kilojoules, right? So to do that, we have 1 kilojoule over 1,000 joules. So that way atoms cancel, joules cancel, and then we end up only with kilojoules per mole. So if we do that in this case, so have our number right here, take this and multiply that by Avogadro's number. So 6.02 times 10 to the 23rd divided by 1,000. And what we get is, or at least what I got is negative 20,997 kilojoules per mole. Right? Which is pretty close to what the experimental value is, right? 21,004 kilojoules per mole, right? It's only off by, right, 7 kilojoules per mole, right? That's pretty good for something that's, essentially just a simplified, right, a pretty simple equation, right, to get to that value, right? And that just shows the power of like how accurate it actually is. In this case, right, you guys are able to calculate it, which is great. Right. And one thing to think about, right, is that we know that the energy level, right, of anything is always going to be equal to the negative of the ionization energy, which is why energy levels are always going to be negative numbers. Ionization energies are always positive numbers in these cases. So that's how you work your way through all of these